All right. Thank you everyone for coming. Today we are here for Max Ehrlich's thesis defense. Thank you for all the committee members. Larry is his advisor. Wojciech Jaha is the dean's representative. We have Ramni, Dinesh, who are members from UMD, and we have Michael and Professor David Forsyth from UIUC, Michael from SRI, who are external members in the committee. We follow the standard protocol where Max will present and committee members can interrupt in between. For audience, towards the end, we'll have some time for audience to ask questions, then we'll respectfully kick you out, and then we have just the committee with Max. Okay. With that, we'll let Max start, but I just wanted to say a few words. Max is one of the students I inherited from Larry. And he used to work in an area that I had no idea about. And now I think 3 or 4 people in my lab work on those ideas, and Max is primarily responsible for that. He has branched out from the niche that he used to work in, and we'll talk about some of the branching out that he has done. But he is one of those starting junior advisors that I'm happy to have in the lab. He manages his own lab. He has his own mini lab meeting, which other students are jealous of because there's some senior worker meeting with them. So you will see some of those flavors come out today and stuff. So with that, Max, off you go.
Okay, wow. Thank you for the introduction, Abhinav. And yeah, so thanks for coming. I'm going to do my thesis defense now. And, ever since COVID happened, it was kind of my dream to have an in-person defense. So I'm really happy to be here. And I think Abhinav did a good job of this, but I am going to just briefly introduce the committee here. So, chairing, we have my advisors, Abhinav and Larry, and I think you guys don't need much of an introduction. Half the people in this room are Abhinav's student anyway. So serving as the dean's representative, Professor Wojciech Chaya, thank you so much for being here. Professor Chaya is from the mathematics department. He's an expert in harmonic analysis. And we have 2 external members today, Dr. Michael Isnardi from SRI International, who is an expert in compression technology, and Professor David Forsyth from UIUC, who is an expert in pretty much everything computer vision related. And thanks so much for being here, guys. And our 2 internal members, Professor Ramani Duraswamy, who studies these biologically inspired acoustics models, and Professor Dinesh Minocha, who is a computer graphics and simulation expert. Okay. So I'm going to start off with a quote today. Hope you guys can bear with me while I read this. In the history of AI and pattern recognition, ad hoc engineered methods have often worked better initially before data and compute power was available to rely increasingly on ML. It happened in OCR, ASR, CV, MT, NLP, and now in robotics. So this was written by someone you guys might have heard of. His name is Yann LeCun. And this was last year. I believe he was responding to a tweet where somebody had benchmarked a set of reinforcement learning techniques. And they had found that the carefully engineered methods were still outperforming machine learning based methods, but the gap was starting to close. So people who know my background and know the research that I do can see how this kind of statement would kind of rub me the wrong way, especially coming from a leader in the field like Yann LeCun, because it kind of sets up this engineering versus science dichotomy, right? Where you have this traditional pipeline that scientists do some science, and then engineers take that science and make something work. So science informs engineering, but can engineering also inform science, right? And I think this is much more reflective of the way that the real world works. You have this kind of feedback loop where science leads to engineering, leads to better science, leads to better engineering. So in particular, there's many interesting scientific problems that are well grounded in engineering, and compression is one of them. That's what we're going to be talking about today. But I think the bigger point I want to make is that I think that the general machine learning methods that Yann LeCun is talking about are really important. And they're really interesting, but they're not what I've chosen to study, and that's okay. I'm not going to go calling those things ad hoc on Twitter. I think there's room for both of these perspectives in the field. So this is the kind of, yeah.
Deep learning, by your definition, science and engineering.
I would say it's a mix of both. Yeah, it's treated very much like an engineering problem by some people, by other people, by science. And that's kind of a cool thing about it, is it straddles those 2 disciplines. Okay, so this is the kind of high-level research philosophy that I'm trying to talk about here, which is this first principles approach to science. So when we're working on these engineering motivated problems like compression, there's all these engineering decisions that went into the design of the problem, and we're going to call these decisions first principles. And we're going to take those first principles into account when we're developing our algorithms. So I don't think that this is a new idea either. This isn't something that's going to revolutionize science. I think this is the way most people are already going about their science, right? For example, Professor Ramani studies these, biologically inspired acoustics models. So he has prior knowledge of the problem and he uses that to improve his acoustics model. So it's the same kind of idea here. Okay, so that's just something to kind of keep in the back of your head as I'm going through the technical portion of the talk. And now we're going to talk about the internet. So the internet is this really incredible thing, and I call it a repository of human knowledge, right? So the biggest problem with facing the internet today, in my opinion, is that there's this inequity in how the internet is accessed. So Pew Research did some study on this, and they found that about a quarter of people don't have a broadband connection at home. And by broadband connection, we're talking like faster than dial-up, right? And of course, like many things in America, it breaks down on racial lines. So Black and Hispanic respondents were less likely to have a broadband internet connection than white people. So there's a couple of problems with these charts. One is that there's more races than white, Black, and Hispanic. But the other is that it's not really taking location into account, because we know that rural locations are heavily underinvested in by telcos. We know that Native American reservations have almost no broadband infrastructure. And we know that people outside of America are facing this problem as well. So I'm going to make this kind of claim that society as a whole benefits from maximal internet participation. And we can't talk about the internet without talking about multimedia, because this is how so much internet interaction happens these days, and particularly videos. If you think, when was the last time you went to a website and there wasn't a video on the page somewhere, or at least an image, right? And again, Pew Research has studied this, and they've done a really great job kind of mapping out the landscape of the internet. And in particular, when we talk about videos, it's projected that this year, 82% of consumer internet traffic is going to be coming from videos. So it's had this really explosive growth. And the problem with this is that images and videos are hard to receive if you have bandwidth limits, right? So if you don't have a broadband connection, it's hard to view multimedia. And if you're on a metered connection, that gets even harder, because now it's like, if you want to watch a 250 megabyte YouTube video and you pay $10 a gigabyte for bandwidth, is that video worth $2.50 to you? Right? Something that we kind of take for granted as being free. And this is very common in rural places, to have a metered connection to your home. So the way we get around this is with multimedia compression. And when we look at what compression is actually being used, it's pretty much JPEG for images and H.264 for videos. So the problem with this is that when we look at, like, JPEG turns 30 years old this September, and H.264 is 19 years old. This is ancient history, right, in computing terms. And we have better stuff now. We have better stuff, especially for videos, right? We have H.265, which was like totally skipped over. AV1 is getting some traction, but it's still not common. And all of this is going on in the backdrop of this global pandemic, where your work and your school are online now, right? So if you don't have a broadband connection at home, that means you might not be able to make a living, means you might not be able to keep up with your studies, and it's going to affect the whole trajectory of your life. So it's a major problem. Meanwhile, we have deep learning, which has come on the scene, and I guess it's not new anymore, but it is revolutionizing all these problems, and compression is no exception to this. So this is a very famous paper from NeurIPS 2020 called Hi-Fi-C. And what's going on here is really remarkable, because the Hi-Fi-C result is actually smaller than the JPEG. And I don't know how well this is coming through on the projector and stuff, but you can see that the JPEG looks like garbage. And the Hi-Fi-C result looks like it was never compressed. So why aren't we using this stuff, right? We have an internet which is increasingly focused around multimedia. We have people that have trouble participating in the internet because multimedia files are too large. We have better classical compression. We have really incredible deep learning compression. Why don't we use it, right? And the answer is twofold. It turns out if you're a company and you process a lot of images and videos, you have this really complex pipeline that handles that. And it would actually be very expensive to go in and pull that pipeline apart and build it up around another compression algorithm. Also, especially when we're talking about the deep learning side of things, we really want to standardize these things into codecs so that everyone's operating from the same place. And codec development is intentionally a really slow and deliberative process because it needs to meet everyone's needs. So as great as this Hi-Fi-C result is, it took me 5 minutes to compress this on a V100 GPU. The JPEG took less than a second on my laptop from 2017, right? So the JPEG is meeting more people's needs right now. That's the bottom line. So what's my kind of big idea here? Instead of trying to replace the classical codecs, we can try to work with them to improve them. And the big advantage of this is that we're going to be able to use this stuff in real applications in the near term because there's no special software required, right? We can tell the data center, all you have to do is take a little module with our code and add it onto the end of your pipeline and it'll do the work, right? You don't need to tear your whole thing apart. We can tell users, if you don't have the resources to run a deep network, at the end of the day, you're still just getting a JPEG. So you can view it, it'll look worse. And the interesting thing is that when we start considering the idiosyncrasies of these compression algorithms, we open up a whole bunch of really interesting problems like compressed domain deep learning, improving deep learning accuracy on compressed images. And we're going to talk about these topics today. And in all cases, we're going to leverage what we know about the compression algorithms to inform the science we're doing. Okay, so let's dive right into it with the compressed domain deep learning. So the idea here is this is a network which is going to take compressed JPEG data and do a convolutional network on that without any decompression. Why you might want to do this? Well, JPEG decompression takes time. JPEG data is sparse, so decompressing one JPEG is fast. But if you had to do, let's say, a training run with millions of JPEGs, that time adds up. And if there's some sparsity you can exploit, that would be nice too. But the idea here isn't just that we're going to have some model that sucks up JPEG data and then does something. We want something that has some guarantee on the underlying pixel domain network. So if you look at the pipeline here, the top here is kind of your traditional pipeline where you have a JPEG, decompress it to an image, CNN processes it, and it outputs some logits used to make your decision. So what we want to do is take that same CNN and somehow transform it using an algorithm we're going to develop such that it can take the JPEG data in without decompressing it and output the same logits. And we can kind of do this. We can't get exactly there. We're going to talk about why. But essentially what this means is we have to math this out, right? We have to figure out how to reformulate this. And specifically, we're going to be taking or making use of this idea that JPEG is essentially a linear map. And if that sounds ridiculous, it's fine. We're going to talk about it because it's a little counterintuitive. But if we assume that JPEG is a linear map, then any linear operations we do can be composed with the JPEG linear map. And then we have a compressed domain version. So we have to, we're going to be working with this simplified ResNet today. This is the res blocks, and then there's a global average pooling and fully connected layers. So this is like your oversimplified ResNet. So what we need to reformulate is the convolution, which is linear, so that's composable. Batch norm, we know how the statistics transform through this linear map, so that's also, we can do it. The sum, linear, we can do it. The global average pooling is again statistics, so we can do it. The ReLU is the problem because the ReLU is nonlinear. So we can't compose it, and this is where we have to rely on an approximation technique, which is why I say that we can't get exactly the logits we want. So now we need to talk about what JPEG actually is. So what I've done here is I've written basically the four like high-level steps of how JPEG works, and the real like meat of it is this step one where you compute the DCT on non-overlapping 8x8 blocks. So this is a frequency transform. There's a few reasons that you would want to do this. And I just want to make clear by frequency transform, what I'm essentially talking about is the real part of a discrete Fourier transform. Okay, so the reason you do this is twofold. One is it does reduce the entropy of the signal a little bit because it pushes the data such that the magnitude is consolidated into the top left corner of each block. The next reason is that we know that the human visual system responds less to high frequency signals, which means that if we want to remove information from the JPEG, we can get rid of high frequencies, which is what the next step does, where it divides by a quantization matrix and rounds, right? That rounding is the lossy thing, the main lossy thing that happens in JPEG. And that rounding is removing information, and it's specifically from the high frequencies guided by this quantization matrix. So you'll notice that I highlighted some of these steps in red. These are nonlinear steps. So the entropy coding and the run length coding and this rounding, these are the nonlinear steps. So we're going to make a definition now, which is what is the JPEG transform domain, which is everything in this red box, basically. So output of step 3 or input to step 2 here in the decompression. And this is a standard definition that's been used from the 90s. This isn't my definition. The next change we're going to make is we're just not going to round because we're in charge of how the compression happens. It's our choice when and how to round. So we're just not going to do it. And if we do that, then compression is linear and decompression is linear. Okay. And the way that we define those linear maps is using tensors. So this looks kind of complicated, but the way it basically works is that, if we say that an image is in this tensor space and then transform coefficients are in this tensor space. And by the way, this is exactly what something like PyTorch is already giving you, just written with actual math, like correct math. Then we can define the steps of JPEG using these tensors here, which again, just in the interest of time, I'm not going to go into a lot of detail about how this works. So then we can compose this using this expression here. This is written in Einstein notation. So what this means is that the stuff on the top here is an index, it's not a power. And if we see a power on the bottom and the top, there's an implicit sum here that sums out those indices. Okay, so this gives us a JPEG compression and JPEG decompression tensor, which means it's really easy for us to make a compressed domain convolution, right? We're going to use what I call NLS to do that. So we write the naive steps. If we were going to do a convolution on a compressed image, we would decompress the image, convolve, and then recompress. Then we write those steps as linear maps, and then we start substituting, right? I here, I prime here, which gives us this result here. And this chi here, I think it's chi. I picked it because it looks cool. This is the compressed domain convolution, which goes from coefficients to coefficients. So that's it. That's all we have to do. So the next thing we want to talk about is the batch norm and global average pooling. And again, in the interest of time, I'm not going to go into huge detail about this, but the main result is that the 0,0 coefficient. So remember, I said the DCT happens on 8x8 blocks. So the top left coefficient of each block is proportional to the mean of the pixels that were in the block. So if we want to form a global average pooling vector, all we have to do is read that off, and that's our vector. Very fast. And then batch norm has a similar thing going on. It has mean and variance and then some linear operations. So it's pretty straightforward. But then that gives us our problem child, which is ReLU, since ReLU is nonlinear. Sometimes you can do some fancy algebra with nonlinear functions, but in this case, it's very difficult because ReLU is piecewise linear. So in order to pick the right one of these, we have to know what the underlying like pixel or feature value was. So the idea to do this is to do an approximation using the lowest frequency coefficients, because that gets you your most accurate reconstruction. And you'll see, just as I've written this out two ways. This is the definition of ReLU. I think most people are used to looking at this side here. What I've done here, this H is the heavy side function. If people are familiar, that's 0 for negative and 1 for positive. So these are the same. And this is going to be more useful for us in the next slide, because now we have another problem, which is that what ReLU does is it changes negative values but leaves positive values alone. So if we were to do this, we would be screwing up positive and negative values because we're using an approximation, right? So if we look at this image here, green is negative here, red is positive, and blue is exactly 0. So if we compute ReLU on this, we see we just turned all the greens to blue and we left the reds alone. If we did the approximation I just described, then we have some problems with the blues because it's an approximation, but also these nice 2x2 red regions are now all broken up. So it'd be nice if that didn't happen. So instead, what we can do is we can essentially compute this heavy side function on the approximation, which is essentially a binary mask. It's 0 for negative, 1 for positive. Then we can multiply that mask by the original coefficients and we get something like this. So again, the blue regions are still kind of wrong in some places, but at least the red ones are preserved now. But we have a new problem because we have coefficients as input and we have a mask in pixel space, right? So we have to somehow multiply these together, and we can again do that with NLS. So I'm not going to go through this one in detail, but you end up with this H here, which is a bilinear map, which takes the mask in pixel domain and the coefficients in the transform domain and outputs coefficients after pixel-wise multiplying them, basically. Okay, so how does this work? It does work, first off. And what we have here, so this is throughput. So the JPEG inference is much faster than the spatial domain inference. And the JPEG training is a little bit faster. It's very close, but it's a little bit faster. What we have here is measuring the accuracy of this ReLU approximation that we did. So green is our masking method and yellow is the naive approximation that I talked about initially. We can see in this graph, what I've done is I've trained this toy network on pixels completely and then used the formulations in the previous slides to convert it to work on JPEG data with a varying number of frequencies in the approximation. And you can see that like ours is generally performing better. And you can also see how many frequencies it takes to get like a decent result. With this graph, what I've done is I've just trained from scratch on the JPEG with the JPEG formulation. So you need less frequencies to get a good result there because the weights actually learn to cope with that approximation. And yeah, again, the masking is doing better. Okay, so now we can do something that's a little bit more straightforward. We can just try to improve JPEG compression. So the goal here, again, this speaks right to what I was talking about at the beginning of the talk, which is to compress an image at really low quality and then have a neural network correct it. So you get this kind of have your cake and eat it too situation where you get like a JPEG. And again, I can't tell how well this is coming through, but the JPEG looks really bad here. The network makes it look a lot better. There's my cursor, there it is. So this isn't exactly a new idea. There's some problems with prior works on this though, and we're going to talk about what those are. So first problem, biggest problem, is that prior works are doing what they call quality dependent models. So when you save a JPEG file, sometimes you'll get like a little pop-up. I don't know if you've seen this where it asks you what quality you want to save it as on 0 to 100 scale. And the higher quality looks better, but is larger. The lower quality looks worse, but it's smaller. So it turns out that this actually has a pretty big effect on how the degradation is applied to the pixels. And if you just gave any random JPEG at any quality over to a network, it's unlikely that it would do a good job. So the way people were getting around this was they would say, I'm going to train a model that just does quality 10 JPEGs. and I'll train another one that just does quality 20 JPEGs, and another one for quality 30. So this is impractical, right? It's hard for people to train one network, let alone however many you would need to correct all the JPEGs. So it's impractical for another reason too, which is that quality isn't actually stored anywhere. Remember when I was going over the steps of JPEG in the last section, there was no mention of quality. We talked about a quantization matrix. So what the encoder is doing is it's actually computing the quantization matrix from the quality. Then the quality goes right in the garbage can, and what's saved in the file is the quantization matrix. So our solution is, first of all, we're going to use one network, which takes the image and its quantization matrix as input, and it kind of adapts what it's doing to the quantization matrix. So, okay, so the next big problem is that prior works were almost exclusively doing these grayscale only models, which is a problem because real images are colored, right? Generally. So when you save a JPEG, what JPEG is doing is it's actually saving it in a color space that separates the brightness information from the color information. So we call this YCBCR, where the Y channel is your brightness, CBCR are two color channels. And the reason that it does that is that the color information, or the human visual system, responds less to small changes in color information than brightness information. This means that the encoder can further degrade the color channels in order to save more space. And usually it does what's called chroma subsampling, which means that it saves the color channels at like half the resolution of the grayscale channel. So this is much more degraded than the grayscale channel, and it means that a model trained on grayscale isn't really applicable to color images. So our solution to that is to explicitly handle the color channels. And in particular, we're going to give it the restored grayscale channel so that it has that extra information that isn't present in the color channels to guide its restoration. Okay. The final kind of problem here is that, again, almost exclusively, prior works were doing this error-based regression, which gives you a blurry result. So this is like your L1, L2 loss function. And there's a couple reasons for this. One is that that's just sort of a natural phenomenon when regression networks are trained. But the other reason is that we've been talking about how JPEG removes high frequency information. And that's where your like texture and stuff lives, in that high frequency space. So it's really hard for the regression network to restore that. So what we do is we have a GAN loss, which helps by its own, but we also have a formulation that specifically targets textures. And we're going to talk about how that works. So the first thing to talk about, though, is the quantization side data. So this is, we use this convolutional filter manifold for this. And again, the quantization matrix is an 8x8 matrix, right? Because you element-wise divide by the DCT block. And what we have here is essentially a mini convolutional network, which takes the 8x8 input and produces a weight of its own, which is then convolved with the input features. So essentially what's happening is, instead of a weight that is a function of just the input and output features, it's now a function of the features and the quantization matrix. So it can adapt to different quantizations. And we're actually going to take a quick detour and talk about these more, because I never get to talk about it. So I wanted to talk about it now. And it's like my favorite thing, because these things are really cool. They do really cool things. So yeah, just bear with me for a minute. So what I've done here is I take JPEG quality 1050 and 100, right? And I generate the quantization matrix. So I generate this Q, and then I put this Q through a fully trained network and pull out W for one channel, or sorry, for 3 channels here. One layer, 3 channels. Okay? That makes sense? So what I've done here is I'm literally just taking these W's and I'm heat mapping them for the different. So quality, as we can see, as we increase in quality, it's the same basic shape that's learned, but the magnitude of the coefficients is decreasing. And this makes sense because for a quality 100 image, we don't really have to do that much to it to make it look good. So the kernel entry should be smaller. But it's neat that it learns the same basic shape. And then the other thing is, if I take these 9 filters and then just using gradient ascent, compute an input which maximizes their response, I get something like this. And this is really cool to look at because what is this? This is JPEG artifacts, but without an actual image, right? And again, we can see as the quality increases, the magnitude of the artifacts gets smaller. And at quality 100, it's basically the same as my input, right? It hasn't really done anything to it, which is kind of neat. There's one other way we can look at this, which is to take all the quantization matrices now and project them into 2D and plot them. So what we have here, right? We start off with very different behaviors. And then as the quality increases, the weights become more and more similar until at quality 100, they're basically the same, which is to say they're not doing much because they shouldn't have to be doing much, right? And the cool thing about this too is that the circled points here are points that the network saw during training. So even all these intermediate points that it hasn't seen, it's able to place them in the right spot. So it's really learned a relationship on the quantization matrices. Okay, so that's my detour. We can go back to the network now. Okay, so one thing we have to consider here is with the quantization matrix, what we have is basically describing how much rounding happened to the coefficients. So what we really want to do here is coefficients to coefficients. We don't want to do pixel to pixel, so we don't have that relationship. So that's what our network is based around. And this requires a couple tricks for reasons I won't get into. Giving this over to like a 3x3 filter won't work well. So there's 2 things we can do. One is the block representation, which is an 8x8 stride 8 layer. So remember the DCT is computed in 8x8 blocks. So this is taking each block and computing some representation, and then you do whatever you want with that. The next thing you can do is the frequency net, where you take those blocks and just flatten them into the channel dimension. So again, you get like a 1x1. This time it's by 64. And then when you do your convolutions, you do them in 64 groups so that it's like each frequency gets its own mini convnet that processes that frequency in isolation. So we use both of these to restore just the Y channel, so just the brightness information in this step. Okay, so the next thing we do is the color channels. So we said that the color channels are often chroma subsample. So that means we have to start off with basically a mini super resolution here, where we just do some processing and then upsample this so that it's the same spatial resolution as the brightness channel. And then we can give it that extra brightness information, do some further processing to get the restored coefficients. Okay, and then the GAN and texture loss. So the GAN is like pick your favorite GAN, that's standard, but the texture term is kind of interesting. So the way this works is oftentimes when you're doing a restoration task using a GAN, you have what's called a perceptual loss, which is like a VGG network trained on ImageNet. And you want the response from the network output and the true target image to be close in this space. So what we're saying here is we know texture is a problem. So what we're doing is we have a VGG network, which is trained on the MINC material classification data set. And the idea there is that if the response is similar in material classification space, probably these 2 things would be classified as the same material, and they probably have similar textures. And we'll show how that works. But quickly, just flashing the numerical results up here. Ours is orange and we're beating these guys. Thing to keep in mind with these guys though is that they train, like I was saying, quality dependent models. So like this green was trained just on quality 10 images. Our network was trained on 10 to 100 all at once, and it's still able to beat these guys. And because it's so easy to run our network on different qualities, we can show the result for 10 to 90. Above 90, it's kind of negligible. And we can see the improvement over JPEG throughout the range. Okay, so now what you really want to see, which is the qualitative results. So, key things to keep in mind here. This is the input, right? This is the JPEG. Regression is if I only train with an L1 loss. GAN is when I include the GAN and texture losses into the mix. So kind of cool thing here, this lighthouse is supposed to have a wraparound railing, which was pretty much destroyed by the compression, but the network has sort of put it back in, which I thought was kind of neat. And then down here on the bottom, you can see the comparison with the GAN. It's like night and day, because we actually have this nice rock texture, these nice sharp edges and leaf textures, and it looks way better. Okay, here is a really high resolution image. I don't know how well this is coming through at all, but there's banding. Can you guys see this at all? No, maybe the light is too bright. Yeah, we can turn the lights off.
I can see it on Zoom.
You can see it on Zoom. Okay, you see it now? Okay. Yeah, so the banding on the foreground and background, which is cleaned up by the network. And then this is a nice one where you can see a lot of really heavy banding going on around the light here, which is cleaned up. And this is apparent even when zoomed way in. Right? So, okay, so now we can talk about a little extension to this work, which is for machine tasks, right? We've been talking about restoration for human consumption, but what about machine consumption? And this is important because deep models are being deployed into these consumer settings, and we really have no idea if they're actually working well or not. And it's hard to benchmark this just with academic data sets because there's not a lot of compression going on. So we want to know, how do deep models cope with this quality loss? But more importantly, can we do anything about it? And we did this giant study with like 27 models or something in different tasks, and I have it on the right. We're not going to go into the study because it's a bit of a dry topic. But what I do want to talk about today is the task targeted artifact correction, which is your artifact correction for machine tasks. So how does this work? So we're going to fine tune the artifact correction network using loss from some downstream task. So we take an image, pass it through the task and record its logits. Then we take that same image, JPEG compress it, artifact correct it, pass the artifact corrected version through the task and record its logits. And the loss supervision here is the error between these two logits. This is backpropagated all the way back to the artifact correction network. So this is kind of cool because it's really flexible to use and to train. In particular, it's totally self-supervised, so you don't need labels to train this at all. We're only dealing with logits here. So you just put whatever images you want, make the logits match. The next thing is, because the task isn't touched at all, it's just the artifact correction network that changes. You can take this artifact correction network and use it for other tasks, right? And it does work on other tasks. So you can train it on like a mobile net and then use it for like mask RCNN, and it'll actually do a decent job. You can even train it with multiple tasks at the same time to get even better generalization. So how does that look? So here's some charts, and the way to like kind of read this is, you know, the green line here is I've trained the artifact correction network on MobileNet, and then I'm testing it on ResNet 101. And we can see that it does a decent job. It's almost matching if I trained on ResNet 101 and tested on ResNet 101. And that's, you know, true throughout here. And again, this is, you know, if I go over this, this is a semantic segmentation model. What I have here is I've trained this MobileNet, which was trained on ImageNet, and now I'm transferring it over to a semantic segmentation, which is like a totally different thing, right? But it still works. And then down here is the multi-head setup. So for two tasks, again in green here, let's say, I've trained this on ResNet 50 and faster RCNN, and then I'm testing it on the ResNet 50 for ImageNet. And again, this is actually outperforming just training with ResNet 50 because it's able to generalize better, right? And in case it wasn't clear, lower is better here. And also the blue line is if we were to just take this task and fine tune it with JPEG inputs, right? So oftentimes that fine tuning works better, but not always. Sometimes the task targeted is the better thing to do. But yeah, that's that. And we're going to move on now to the last topic today, which is, we've been doing this for images. How about doing it for videos, right? Obvious thing to try. So deep learning for video compression is a thing. It's making pretty good progress. In particular, the last thing I saw was from Wave 1 at ICCV last year. And they're sort of matching AV1 for rate distortion, but they're like significantly slower. So this isn't going to be really ready for consumers anytime soon. And again, I don't want to sound like I'm disparaging Wave 1 here. The result was phenomenal, but it's just the reality of deep learning these days. It's very resource intensive. So how do we get deep learning and video compression in the near term? Well, we do what I've been saying, which is keep H.264 around. And it has all these great advantages to it that I've been talking about. So again, this isn't a new idea. People have been trying to do artifact correction for compressed videos. And prior works do what I like to call it multi-frame image to image, which means they take 7 frames and they output 1 frame. So you can think of it like a sliding window. If you were to do a whole video just sliding across the video. And this is really slow, by the way. They're also using another kind of standard procedure from restoration tasks, which is this idea that nearby frames should be aligned to each other in order to improve the result. And they're using like optical flow and deformable convolutions for the alignment, standard stuff. One kind of unique idea that came out of this was this peak quality frames idea, which is that since we know that we know what the original images look like, because this is a compression problem, we know exactly what they look like. We can actually measure which frames were compressed to higher quality. So that's what these like red dots are showing for time here. Which ones are the peak quality frames? And we can pull those out and use those to help restore the lower quality frames. The problem is that the way they did this was with another deep model that just went along the video and produced, which ones are peak quality frames, which is again slow. And also look at how suspiciously evenly placed these are. It's kind of interesting, isn't it? So now we're going to talk about how video compression actually works, because we're going to use this stuff in a minute. So we have our entropy reduction in space like JPEG, but also in time. So we have intraframes, iframes, which are just basically like a JPEG. They can be decoded with no external information. We have predicted frames, P frames, which require one previous frame to decode. And then these things are organized into what's called a group of pictures, which is an iframe and his associated P frames. So the iframes are pretty straightforward. They're literally just fancy JPEGs. But what about the P frames? So the P frames, all that's being stored is motion vectors and error residuals. Motion vectors are like heuristic block motion. So this is, think optical flow, but on blocks instead of single pixels. And then the error residual is everything that can't be modeled just from those motion vectors. So if you look, what I have here, this is like the previous frame. So if the decoder wanted to tell you the next frame, it reads these motion vectors and then just copies and pastes the blocks over. So you can see in this one, it's copied and pasted blocks and they look like they're in a different position, but they're not looking perfect. So then it will just sum with the error residual to give you the final frame. And this usually looks pretty good. Okay. So we can use this stuff, right? So first of all, when we're doing the alignment, we don't need to go computing optical flow. We can just use the motion vectors. The next thing is the iframes are what's stored at higher quality. So we don't need to search for PQFs, right? So like the encoder will just put an iframe and then several P frames and then an iframe evenly spaced. And that's what those PQFs were in the last chart. So we can just pull those out and use those. So what is our approach doing? Read the motion vectors to align the feature maps. Use the iframe restorations to guide the P frame restorations. And then we make another optimization, which is to use this GOP structure. So what this means is that our network will take one iframe and 6 P frames, so 7 frames total. And in one forward pass, it'll output 7 high quality frames instead of having to do the sliding window. So that's much faster. And since we made all these optimizations, we can kind of reinvest the parameters into the restoration network, which will bring its speed kind of down to match what prior works are doing, but it'll be much more accurate. And then we do some fun loss function stuff. We'll talk about that too. So phase 1 of how you actually do this is to do a really good job on the iframe. So how do we do this? So we take the low quality iframe, and since this has the most information of all the frames we have, we compute a wider representation on this, 64 dimensional. For each of the low quality P frames, we compute a 16 dimensional representation of it. And then we use these motion vectors to do the alignment. And then we concatenate all of this stuff together into this iframe representation, which is 160 channels, and then generate the restored iframe. Phase 2 is to use that high quality iframe to restore the P frames. So we take that iframe and we take the motion vectors, and going in reverse, we just warp them to match the P frames, concatenate them, and then generate the restored P frames. So, and also keep in mind that I've written this as like 2 separate steps, but it's one network which is trained end to end, and it's, it's all one kind of forward pass. Okay. And then the next thing to talk about is the loss function. So one thing we've been saying is that compression destroys this high frequency information. And in the JPEG work, we used the GAN to get around that. What we want to do here is see if we can do some high frequency restoration, but in a regression setup, right? Which would be nice because it would be accurate. So what we do, and I won't go through everything, but what we're doing is we're basing this on the difference of Gaussian's scale space, which is an idea from classical computer vision, pre-deep learning stuff, where we're basically pulling out different frequency bands, and we're telling the network, instead of just restoring the low frequency band, also restore these higher frequency bands. So we're kind of incentivizing it to do well on the higher frequency stuff. And this does work. It actually works better as a numerical result, which is interesting. It still doesn't really solve the visual problem. So to solve the visual problem, we again do the GAN thing. The favorite GAN has changed in this time, but since we have a video, we can do this temporal consistency with the GAN, which is, if you guys haven't read TechoGAN, highly recommended. It's a great paper. I think it was kind of slept on too by the community. But other than that, the texture loss is the same from JPEG. So quantitative results. Ours is in yellow. These are prior works in artifact correction. And you can see again, we're like beating them. This only goes up, I think, to 51. So yeah. The other kind of interesting comparison we can make is to fully deep learning based compression. So this is a bunch of techniques for just like fully deep learning based codecs. And in terms of decoding speed, where actually NERV is the only one that is beating us right now, but encoding speed is through the roof because we don't need to do any deep learning to encode, right? This is H.264 on a CPU. So that's nice. In terms of rate distortion, ours is this dotted yellow line here. And for the low bandwidths, the low bit rate, sorry, we're outperforming pretty much everybody, and it kind of drops off at the high bit rates, but that wasn't really our focus. I think that's a solvable problem if we wanted to do it. Okay. So now we're going to quickly look at a couple of qualitative results. And this is where, if you're at home, look at the PDF, because Zoom is going to wreck this. It's going to recompress it, and it pretty much wrecks it. So here is the compressed frame. Things to look at here. I think the biggest thing is on the trees, but also like any edges and blurry things are going to get cleaned up. So here is the restored frame. Did you guys see that? Here's some crops so you can see it better. So if you look at the trees, this is the compressed, this is the restored version. Our trees have leaves on them, which is something you want your trees to have. Lots of nice sharp edges and textures. The car isn't a blurry mess. It actually looks like a car. So that's great. So here's another one. Thing to pay attention to here, I would say, would be the roof. So here's the compressed version and the restored version. So the roof has a much nicer texture. Here's the crops, so you can see what I'm talking about. Much more believable texture on the roof and the trees, the back of the dress. Some wonky stuff going on here on the wood paneling. That's okay, it happens. And now we're going to quickly recap. So what have I been saying today, right? Compression is really important. It's what powers the modern internet. And the better we can compress things, the more people are going to be able to participate in the internet. And I believe that deep learning is certainly the future for this, but we're really far off from that. So how do we do this in the near term? We work with the classical compression. And this opens up all these really fun related problems we can solve too. So what's the future of this? Obviously, we want better, faster models. That's something we always want. But there's new problems too. New problems to solve in data security, frequency-aware models, adversarial learning, things like that. And consumer applications, I would say, look for this in the next year or so. We're very close to making these things consumer ready. So that's it for the technical content of the talk now. So I'm just going to quickly show the publication list because that's a thing people do. And everything below the gray line is before I was at UMD. Everything in dark text was presented today. And then I have to just recognize a few people who made this work possible. First of all, everybody in Abhinav's lab has been fantastic, but I want to recognize these 4 students here. You guys, I think I've been working in the longest case for over a year. Is that right, Shashira? You guys have been fantastic, and I cannot wait to see what you guys do next. The students here on the bottom row came to me through the GradCo peer mentoring program, which if you guys don't know what that is, I highly encourage you to look into it. You can get a mentor, you can get a mentee, you can do whatever you got to do. They'll help you out. And I was amazed at what these guys did in just 1 year at UMD. Incredible. I have to thank my advisors, Larry, and without exaggeration, Larry's the reason that I came to UMD. I came here to work with him. He encouraged me to come, and he's been incredibly supportive throughout the whole time. Thank you, Larry. And Abhinav, obviously, staying up until 2, 3 a.m. every conference deadline, doing writing and figures, and not just for like 1 student, but for like 20 some students. I don't know how you do it. I could not pull that off. Thank you. And then I have to, of course, recognize my family, because the last 5 years have been extremely difficult, not just for me, but for all of us. And my wife and my dog have been there the whole time. The other 2 came later. So thank you guys. I love you. I think you're watching from home. And I will take questions now. Thank you.
All right, so we'll do audience questions. Great job, Max. We'll do audience questions first. Anyone on Zoom or audience here, if you have any questions?
I can actually open this up. If you are shy, go to this website and you can send me a question.
In the meantime, yes.
Yeah, thanks, Max.
Yeah.
Great stuff. I have one quick question.
You keep mentioning that these things are super slow, right?
They're pretty slow still, yeah.
And what do you think is that one single thing which can speed it up? Why is it so slow?
Why is it so slow? It's slow because deep learning is inherently kind of a slow thing right now. And there's a few ways we can speed it up. One is like the standard kind of pruning techniques, but I think the big thing is going to be better hardware support. So right now, when you do encoding and decoding of video, your processor actually has special hardware that helps out with that. And that gives it kind of, in my opinion, an unfair advantage. I expect we're going to start seeing that kind of special hardware for deep learning stuff in the near future become a commodity thing. So
what's the ratio of slowness?
Ratio of slowness. I had a throughput slide. I'm trying to think for JPEG if I had something though. I can do better than this. Hang on. So like this is the closest that I have on hand, I guess, which is like if we look at like one of these things in terms of frames per second on a 2080 Ti, and then this is your H.264 encoding speed. So we're talking about like, you know, and this is this result in particular, I did measure on this old laptop too. So, you know, it's a totally different ballgame, basically. Any other questions?
Any other audience questions?
So you mentioned at some point that there was a network that you created on this like over 0 to 100 JPEG.
Mhm.
And then the computation was taken on, let's say, individual quality, at 10 or 20.
Mhm.
So if, let's say, your algorithm was being at just one quality, does that still perform or do you?
That's a very interesting question, and you're not the first person to ask me this. And I don't have any way to show this to you, but it's actually slightly worse. And I believe the reason for that is that the adaptive weight layer needs more data because you're giving the adaptive weight layer one quantization matrix, and it's not really learning anything meaningful in that case. But it's not much worse. It's not much different, but it's slightly. Mhm. Yeah. Anyone else?
Audience? No? All right, then let's thank Max again.
I'm going to cut the stream now.